In this video, we will construct a simple model for the surface temperature of the Earth to help model global climate change. Before we start, here are 3 basic laws of physics that will make understanding this model easier. Number 1, when we talk about power, we mean the amount of energy in a given amount of time. This is why power companies talk about energy consumption in terms of kilowatt hours. A watt is a unit of power, or energy per time, so multiplying watts and hours gives you energy. Number 2, when I mention intensity, I'm referring to power per unit area. This is probably best understood as it relates to sound. When the source of a sound is far away from you, you perceive that sound to be quiet, because the power of the sound has diffused over a larger surface area in all directions. And number 3, power emitted from an object is proportional to that object's temperature to the 4th power times its surface area. The constant that makes this inequality is called the Stefan-Boltzmann constant, named after the physicists who discovered this relationship, and it's represented here by a lowercase sigma. It should be noted that this third rule technically only works for black bodies, or objects that absorb all wavelengths of light. But using this rule is a good enough approximation to get us started in making the model. With that established, we open on a scene of the Sun and the Earth. The Sun emits energy in the form of heat and radiation, a distance of 150 million kilometers from us. We can calculate the power of the Sun using the Stefan-Boltzmann equation. Since the surface area of a sphere is 4 pi times the radius squared, we can rewrite the equation like so. Plugging in T, the surface temperature of the Sun, and R, the Sun's radius, we have a power of 3.8 times 10 to the 26 watts. Now we can use this power to find the intensity of the Sun at our point in space. Intensity is just power divided by the area of the spherical shell over which that power spreads. So we have an intensity given by this equation, and this is referred to as the solar constant, so I'll refer to it as S for the remainder of the video. When we plug in the shell's surface area, given by 4 pi times the distance to the Earth squared, and the power we just found, we receive an intensity of 1,360 watts per square meter. Let's zoom in for a second and imagine these solar waves crashing upon our earthly shore. When the solar radiation hits the Earth, it does so as essentially a flat line. So if we were able to view this in 3 dimensions, we would see it crash as a flat disk and wrap around the entire sphere. As it wraps around the globe, the energy, and therefore the power, will remain conserved. That is to say, power in is equal to power absorbed, which I'll denote here as PABS. We can write P in as S, the solar constant, times the area of the disk that crashes on the surface of the Earth, and we can write P absorbed as some mystery intensity, which we're trying to solve for, times the surface area of the entire Earth. Knowing the radius of the Earth, we can plug in the respective area formulas to simplify the equation like so. And then we'll set those 2 quantities as equal. From here, we can cancel out the pi's to see that S is just 4 times the solar intensity perceived by the Earth. And finally, we'll rewrite I received as 1/4 of the solar constant, which turns out to be 340 watts per square meter. But this isn't the whole story. Not all solar intensity received by the Earth is absorbed by the Earth. In fact, a significant fraction is reflected back to space, but not all of it, and the Earth takes in the rest. This is where we introduce a constant called the global albedo. Albedo is Latin for whiteness, which serves as a good intuition for what albedo actually represents. Albedo is simply a measure of an object's reflectivity, so very reflective things have an albedo close to 1 and may appear white to us. Similarly, very dark objects tend to absorb a lot of energy without reflecting much back, and so their albedo is very close to 0. The albedo of the Earth right now is about 0.3, meaning it reflects about 30% of the energy, and therefore power and radiative intensity, that hits it. Thus, the energy that the Earth truly feels is about 0.7 times the total received intensity, or about 238 watts per square meter. Okay, time for a quick math break where we'll apply the Stefan-Boltzmann equation one more time for now to find a relationship between albedo and the surface temperature of the Earth. Because power is intensity times unit area, we can write the following equality. Now, since both areas represent the area of the Earth's surface, we can simplify our equation down to I absorbed equals the Stefan-Boltzmann constant times the surface temperature of the Earth to the fourth power. But just to define absorbed intensity in more absolute units, allow me to rewrite it as received intensity times the fraction that gets absorbed. Since we found earlier that I received is just S over 4, we can make our final substitution in this equation, and then just do a little simplification. And there we have it, an equation that gives global temperature as a function of global albedo. To see if our model works, we can try plugging in 0.3 for albedo and 1360 for S, and we get an average surface temperature of 255 Kelvin, or about negative 18 degrees Celsius. That's roughly negative 1 degrees Fahrenheit. Okay, so our model's off a bit. What did we fail to account for? The answer lies in the greenhouse effect. Let us now imagine a simple model of the Earth, the Sun, and the atmosphere. The Sun provides solar intensity to the Earth, which I'll call I in, and the atmosphere reflects energy back, we'll call that I out. As a reminder, our goal is to calculate the Earth's surface temperature under this new model. To this end, let's assume that the atmosphere acts like a black body and emits photons based on its temperature. That turns out to be a reasonable assumption. The atmosphere then radiates intensity both upward and downward in equal amounts. But if we assume that the Earth is also in energy balance, then intensity radiating onto the surface must equal the intensity radiating off of and from the surface back up into space. To compensate for this, the intensity out must be equal in magnitude to the red intensity plus the blue intensity. And because this model assumes the Earth's total energy is balanced, these two intensities are in fact equal. Plugging in the intensity we found earlier, we see that this green line means that the radiative intensity of the Earth's surface has doubled with the addition of one greenhouse gas layer. But what if we were to add a second layer? Well, just as before, we will have an I in and an I out, and since they're equal in magnitude, I'll refer to them both as I. The top layer radiates intensity back to space, but also must radiate the same intensity downward to remain in energy balance. The blue layer then must radiate an intensity directed upward, which will have a magnitude equal to the red line plus the yellow line, or 2 times our initial intensity. To remain in balance, the blue line has to radiate 2 times I in the downward direction, which finally reaches the Earth. And finally, the Earth must provide an intensity of 3 times I upward to account for both the intensity reflected down from the atmospheric layer and the intensity directly from the Sun. Do you see the pattern? Try watching this quick animation with 4 layers and see if you can figure out how we can predict the strength of this final intensity arrow as a general function of the number of layers. I encourage you to pause the video and think about it on your own. This last intensity, the intensity emitted by the surface of the Earth due to the greenhouse gases, is equal to the incoming solar intensity I times the number of atmospheric layers plus 1. To make this fit with our old model, we can replace the solar intensity with its albedo-dependent expression from earlier. And since we're assuming that the Earth itself is a black body, we can apply the Stefan-Boltzmann equation one last time to find the temperature as we experience it on the surface of the Earth. From here, we can just do a little bit of algebra, and voila! There you have it, a model for the Earth's temperature depending on the global albedo and the greenhouse effect. But we should caution ourselves. This is just a model, and it isn't a crystal ball. But as the statistician George E.P. Box famously said, all models are wrong, but some are useful. We could make this model more complicated by, for example, accounting for the different wavelengths of light absorbed by each atmospheric layer, but even that wouldn't give us full predictive power. Building a truly perfect model requires us to know the relative position and energy of every individual particle in each layer of the atmosphere and its reflective and absorption properties. That's simply more information than we could ever hope to know at any one time. But building a model allows us to form meaningful hypotheses, make qualitative predictions, and get a glimpse of some of the underlying causes of climate change.